Welcome to the Canadian Academy of Engineering webinar on AI and engineering. This session is mostly being recorded today. We've been asked not to record a piece of that, and you'll be told when that happens. My name is Robert Crowhall. I'm CEO of the Academy. I'd like to welcome everybody who is coming to this seminar. I know sometimes it can be difficult to schedule things in the summer, and we didn't give a lot of you much notice, but I'm expecting a really interesting and thought-provoking set of presentations today. I would like to acknowledge that the Canadian Academy of Engineering is our head offices are situated in Ottawa, which is on the unceded traditional territory of the Algonquin and Anishinaabe people. And we recognize that fellows of the Academy live and work in regions across Canada on the traditional and treaty lands of First Nations, Inuit, and Métis peoples. These lands have been home to Indigenous people since time immemorial and continue to be vital to their cultural, spiritual, and economic practices. The Academy honors the enduring presence, knowledge, and contribution of Indigenous peoples to these lands and waters, and affirms its commitment to advancing reconciliation through work and relationships. So with that, I don't want to take up too much of your time, and I just want to thank the organizers for putting together such an interesting session for the day, and it's my great pleasure to hand things over to Professor Yang-Chuan Liu. Yang-Chuan, take it away.
Okay. Thanks, Robert, for the introduction, and welcome to the 2025 CAE International Symposium on AI for Future Engineering. And this is the first one in the series. And we will bring together leading researchers and practitioners to explore cutting-edge AI technologies and their transformative applications across diverse engineering disciplines. I'm the program co-chair Jiangchuan Liu from Simon Fraser University, and together with co-chair Da-Chen Tao from Singapore University. And we will start our first program for the speeches by Professor Kaoru Ota from the Engineering Academy of Japan. The title is Toward Human-Centric AI, Enhancing Well-Being in Diverse Domains. Professor Ota received MS degree from Oklahoma State University in 2008, BS and PhD degree from the University of Azul, Japan in 2006 and 2012, respectively. She is a professor and MEXT Excellent Young Researcher with Moran Institute of Technology, Japan. She is the director of Center for Computer Science in Moran IT. She is the Clarivate Analytics 2019, 2021, and 2020 highly cited researcher and is selected as GS Presto Researcher in 2021, Fellow of EAJ in 2022, and Fellow of AAIA in 2025. So let's welcome Professor Ota.
Thank you very much for kind introduction, Professor Liu. So now I want to share my screen. It works?
Yes, it works. Everything's good.
Oh, okay, thank you very much for having me today. And it is my great pleasure to give a presentation as a first speaker in CAE International Symposium. So today I would like to share our current research achievement related to AI. And before I'm going to share our research achievement, I would like to take some moment to introduce myself and also introduce our institution first. So, because Professor Liu already introduced myself, I skip this slide. I just joined the EAJ in 2022, and now I'm working in the Muran Institute of Technology, Japan. And I'm also director of Center for Computer Science in Muran IT too. And the Muran Institute of Technology is located in Hokkaido, Japan. Hokkaido is a North Island here, and but Muran is located south part in Hokkaido, like here. And as you know, the Hokkaido has a well-known for its beautiful natural environment, and Muran City is a long history, has a major industry center where there are a lot of steel companies. And the Muran City, near the Muran City, there is a lot of good sightseeing places. For example, Toya Lake is a very famous sightseeing place where the G8 summit held in 2008. And also there is a famous hot spring near the Muran City. It's called Noboribetsu Hot Spring. So if you have a chance to come to Japan, please visit us. And now I would like to introduce about the Center for Computer Science. This center is just established in 2023. And then we have our 3 faculty members in the center, and with 1 professor, 2 professors, including me, and also 1 assistant professor. And then we also have 2 guest faculty members. And also we have many students, like 9 PhD students, 10 master's students, and 3 research students, and also the 8 undergraduate students. Now we are doing a research collaboration with a Canadian university funded by Japanese government. It's called JST Aspire Project. Aspire Project is a research support program designed to build a network among the world top research talent and to promote Japan's participation in the international top research community, and also mobilize future research leaders. And this project just started from 2023, and our research topic is hyperdimensional communication technologies for 6G networks. And the co-PI in Canada side is Professor Ekram from University of Manitoba. And I would like to also introduce some about the EAJ, Engineering Academy of Japan, because I'm only member from EAJ side. The EAJ is established in 1987, and now EAJ have 808 fellows, and also 65 foreign fellows. And in the EAJ, I'm belonging to 3 committees, and SDI 2050, Young Scientist Committee, and Diversity and Inclusion Committees. And I'm doing a secretary of the first committee, and in this May, our university hosted a symposium, and we had a lot of participants, like this picture. And also, after I joined the EAJ, I have a good opportunity to attend the Young Leaders program at STS Forum 2022 in Kyoto. In this program, we have a chance to have a discussion with Nobel laureate, and we also have a discussion with young leaders from not only Japan but also from abroad. Now I would like to go into sharing our research achievement related to AI. Today, I would like to share the three dimensions. The first one is the applications for disaster response. And the second one is 60 networks supporting for diverse user requirements. And the third one is the AI-empowered music transcription. Due to the time limitation, I don't go into explain in details. So if you are interested in our research, please look at our published papers, because those are already published in conference venues. The first one is UAV-based semantic communication for disaster response. It is just published in this month, the ICCCN conference. So as you know, that Japan is a famous country where there are a lot of earthquakes happens. So we already have a good disaster response system. It is called J-Alert. J-Alert is an emergency warning system in Japan. And J-Alert sends out warning notifications through TV, mobile phone, and radio, and many kinds of medias. It's just before the disaster happens, like in a few seconds. And then not only in Japan, but also in the other country has a good system. For example, in Hungary, there is an emergency and disaster information services. It visualizes the disaster and the emergency events that occurs on the earth in the real time. And this is a roadmap of a disaster response system. In the very past, if some disaster happened, it takes a very long time, like a month. And this time is getting shorter and shorter. And now, nowadays, we can get advanced warning, like we can get a warning just before some disaster happens, like in second. However, as we know that no one can prevent natural disaster. Natural disasters happen always, so we cannot prevent. So our motivation is like we want to make a robust information and the communication system for disaster response. Like after the disaster happens, we want to communicate with survivors in the disaster areas. So there is three typical disaster network scenarios. The first one is the base station is arrived. However, there is a lot of requests to send, so the network is kind of congested. The second one is a partial network is arrived. So some survivors cannot send a message because some base station is not working. The the case is all the base station is get damaged. So the all users in the disaster area cannot get the communication. In this research, we consider about the scenario 2, the partial network is working. In this scenario, we use a UAV for a function as a flying base station to enable wireless network communications. So the benefit of using a UAV is that from the UAV, we can take a line of sight links. And also we can deploy a very fast and flexible. This is a benefit, but also we have a limitation because of the UAV. It is bandwidth is limited. Also, UAV's energy is limited comparing to the fixed base station. So to overcome limitation with semantic communications, we to overcome this limitation, we use semantic communications. Semantic communication is focusing on the meaning of the transmitted information rather than the exactly transmission of all data. So existing works can be categorized into 2 parts. The first one is full data reconstruction, and then the second one, task execution. So in this work, we consider about the full data reconstruction, and we also assume that all users send a text message because it's emergency scenarios. So this is a system model in our paper, and UAV has a semantic encoder. So this UAV collecting all information from users and encode all data to compress the raw data. And then the UAV sent to the base station that the encoded data, then the base station decoded data here. So in this scenario, we propose deep reinforcement learning based method that optimizing the 2 aspects. One is a UAV's flight trajectories. The second is how to allocate the bandwidth to the users to enhance service fairness. We formulate optimization to maximize the average minimum throughput among the users. I skip the details, and we use a Markov decision process to solve the problem. And then this is an algorithm to solve the problems and to optimize the optimizing the policy for UAV trajectory and resource allocation programs. And we did a performance evaluation by the simulations.
Yeah, okay. Okay. Okay.
And then we compare the 4 baseline strategies. This is a simulation result. It shows our proposed method can improve the overall throughput comparing to all other baseline methods. Okay. So I'm going to the second, our research achievement. The second one is RIS-assisted 6G user diversity perspectives. this work is presented in IEEE Smart Cloud 2023. And as you know that in communication, we are in the 5G stage, and we are going to 6G 2030. And we are expecting more throughput and high-speed internet in increasing data rate because of the many applications like a virtual reality, remote surgery, and self-driving systems. So there is multiple users have different requirements for transmission speed, and these requirements change over time. So in this paper, we consider how to allocate communication resources according to the diversity of user needs with limited communication resources. And we use reconfigure intelligent service technology. The RIS can control metasurface with massive passive elements, which can achieve intelligent wireless environment by dynamically tuning the signal in reflections. And we use traffic prediction to adjust the risk beamforming direction and allocating appropriate communication resources to different user requirements to improving QoE for users, for each user. So we propose a DRL-based algorithm. This is a very simple, but a very effective. In the first step, we predict the user demand based on the historical data first, using LSTM, and then we adjust the risk configuration based on the prediction results, and then we enhance signal to noise ratio through risk beamforming to improve user QoE. And the simulation results show that our proposed method can improve the QoE comparing to random method and also DRL-based algorithm, but without the prediction process. Not only QoE, but also transmission rate is the almost the same performance give up same performance with the other methods. The last one I would like to express about the AI-powered music transcription techniques. This research is also just published in this month, 2025, in HPCC 2025. Automatic music transcription, AMT, is an important part of music information retrieval. AMT is a process of converting an acoustic music signal to some form of music notation like this staff notation. Not only this traditional notation, but also MIDI notes and the piano roll is including. However, the current AMT has three problems. The first one is we need paired music data and MIDI data for AMT. But those data exist independently, and the small amount of data is just paired. The second one is we need a lot of training data if you use a complicated model like transformer. The third one is it is a lack of low resource instruments data. Data volume are very different by instruments. Like piano has a lot of data, but other instruments like flute, guitar has less volume of data. So we propose a new method. It is simple but very effective. We propose an unsupervised training method, which relies only on the MIDI data. So we don't need to pair the music data. And okay, maybe it's almost time. So right, and also we use data enhancement method, and then we also propose the instrumental transfer method. We use a single note audio, just single note audio, and we combine it with the synthesized data. And we place the single note audio in the corresponding position through MIDI information. This is very simple idea, but it's very works well. And after that, we propose a new model with a latent transporter module that synthesized music data is converted to metal spectrogram like this. And then we train the data, we get finally get MIDI data. And we did a performance evaluation and compared the recent other works. And then after comparison, we find our proposal method get a best solution in terms of generalization ability, and also we can with a low resource instruments data, we also get a very good quality of music data. So the conclusion, human-centered AI is emerging as a powerful tool for enhancing quality of life. And I introduce an engineering-driven AI application across diverse domains from 3 aspects. And those highlighted how AI can be optimized to serve real-world needs under resource constraints, adapted to user diversity, and support both critical infrastructure and creative expressions. Thank you very much for listening.
Okay, thank you, Professor Ota, for the excellent talk. And for the audience, we have a QA button in the Zoom. If you have any questions, you can always click that button and submit your questions, and then I will ask on your behalf. And given the time limit, I will take 2 questions from the audience. Professor Ota, one audience asked what challenges exist in maintaining connectivity when ground infrastructure is damaged? If damaged, how do you maintain the connectivity?
You mean the first research
Yeah,
about the because we it's thank you very much for the question, because every base station have a chance to get damaged, so we try to use a UAV, because the UAV can always be fly to the disaster area. So if any base station get damaged, we can use the UAV for flying base stations.
Okay, that's good. And also another question is that is the policy learned mainly from historical data or through online interaction with the dynamic disaster environment? So in the disaster environment, it's from the history data, or you do online learning?
It's online learning actually for the disaster case.
Okay, yeah,
Yes.
that's good. Yeah.
Thank you very much.
Yeah, thank you very much. And thanks for the excellent talk. Then we move to the next one. Thank you. Yeah.
Thank you very much.
Yeah. And again, thanks, Professor Ota. And we come to the next talk by Professor Da-Chen Tao. And Da-Chen actually is also the program co-chair of this first CAE Symposium on AI for Future Engineering. Spent a lot of effort. Minutes, and then we come back. You can stay in the session. Those audience, you can stay in the session. Okay, thank you. Bye.
Okay, thank you. Bye-bye.
Yeah, bye. Shall we start?
Yeah, I think that would be a great idea. So like to welcome everybody back. We've just taken a 15-minute break, and we're going to launch into the next part of today's symposium. So Professor Liu, I'll hand it back to you.
Okay, thank you. And I'm Jiangshan Liu, the co-chair of this CAE International Symposium on AI for Future Engineering. And we have already had two excellent talks from Japan and Singapore. And then in the second session, we will have three more talks from the Canadian Academy of Engineering Fellows. And the first one is Professor Ling Cai. She's a professor with the Department of Electrical Computer Engineering at University of Victoria. She's a Royal Society of Canada Fellow, NSERC EWS Stinson Memorial Fellow, Engineering Institute of Canada Fellow, and Canadian Academy of Engineering Fellow, and IEEE Fellow. In 2020, she was elected as 2020 Star in Computer Networking and Communications by N2 Women. Her research interests span several areas in communication and networking. She was a recipient of the NSERC Discovery DAS Award. And the University of Victoria's Silver Medal for Excellent Research in 2023. She has co-founded and chaired the IEEE Victoria Section, Vehicular Technology and Communication Giant Society chapter. She is an elected member of IEEE VTS Board of Governors and VP Mobile Radio since 2023. She has been BOG member of IEEE Communication Society and IEEE Women in Engineering. She is Associate Editor-in-Chief of IEEE Transactions on Vehicular Technology and served as Distinguished Guest Editor of both VTS Society and the ComSec Society. And her talk title will be Engineering Tomorrow, Rising AI Evolution. So let's welcome Professor Cai.
Thank you, Professor Liu, for the nice introduction, and thanks everybody for coming. And my talk today is about engineering tomorrow, rising with AI revolution. So since the release of generative AIs such as ChatGPT, DALL-E, the Midjourney, people have been both excited and also very anxious about the onset of the fourth industrial revolution driven by artificial intelligence. The most pressing concerns are whether AI will lead to mass unemployment and the social upheaval, and whether it will ultimately replace humans. Perhaps by looking back at the history, we can find some insights. So starting the late 18th century, we entered the first industrial revolution, an era of mechanization marked by inventions like the steam engine, spinning jenny, and the power loom. That's for the first time, we no longer had to rely on human or animal muscles. Steam and other new power sources let us produce goods and move resources faster and more efficiently. This shift also sparks the rise of new ways to travel and to connect the whole world. Starting in the late 19th century, the second industrial revolution took off, driven by electrification and mass production. It was marked by major breakthroughs like electricity, the internal combustion engine, assembly lines, the telegraph, and the telephone. Electric-powered communication let people exchange information instantly, no matter where you are. So making the world more connected than ever. Our governments, businesses, and families could now coordinate across continents. The mass production and fast logistics boosts our efficiency, increased interdependence among people, and fueled urban growth. Together, these shifts move society away from self-sufficiency and toward more complex, more interconnected systems. The third industrial revolution, also known as the digital revolution, began in the mid-20th century and marked a major shift from mechanical and electrical systems to digital technologies. With the invention of semiconductors, computers, digital communication, and the internet, this era enabled the automation of manufacturing and services, drastically increasing our efficiency. It also gave rise to global digital economies and revolutionized the way people communicate and the way we do our business. The core transformation was the move to information as the main driver of productivity, innovation, and global connectivity. So with the rise of the internet and the global digital communications, a new virtual environment emerged, cyberspace. This is the place where digital data are created, stored, exchanged, and accessed. So our human create a new world, the digital world. These past industrial revolution brought us more health and wealth. So if I ask you the question, do you want to live now as you or exchange your life with somebody 200 years ago? So I guess majority of us would still would rather to live now, right? So even the king or queens 200 years ago probably don't have the same life standard as we enjoyed today, thanks to the 3 industrial revolutions in the past. But these industrial revolutions also came at a very serious cost. For instance, they hurt our environment. We burned too many coal and oil. We cut down forests, polluted air and water, and caused climate change. Socially, this revolution also made the rich richer and left many behind, create big gaps in wealth and trust. People were pushed into hard or unhealthy lifestyles, sitting too much, eating well-processed food rather than whole food, and feeling the pressure of fast urban life. Our nerves is always being very tightened. And with the digital age, we add some new challenges, like particularly the younger generation being glued to screens too long and losing real-world connection. So considering all these costs of the past industrial revolutions, as we are going to step into the next one, we hope the next industrial revolution, the AI-driven one, can be a force for good. For example, driving the shift to renewable energy and the circular economy, addressing our global warming and environment issues, and expanding access to education and health to promote equity rather than divide, and supporting sustainable urbanization, even exploring the unknowns from ocean to space, and enabling many more possible positive transformations. So as now we have already seen the beginning of the next industrial revolution about 10 years ago, starting from about 2011 to 2015. The rise of technologies blurring the lines between physical world, digital world, and the biological worlds. This signaled the first industry revolution, also known as the AI revolution. This fourth industrial revolution is defined by groundbreaking innovations such as artificial intelligence, the Internet of Things, robotics, biotechnologies, quantum computing, so on and so forth. These technologies are seamlessly integrating the physical, digital, and the biological realms, enabling transformative advancements. We witness the emergence of smart factories operating autonomously, personalized medicine tailored to individual needs, and the data-driven decision-making at unprecedented scales. Fundamentally, this revolution represents a new era of human-machine synergy, where collaborative intelligence drives smarter and more effective decisions. In this fourth industrial revolution, technologies are breaking down the barriers between physical, digital, and biological worlds. Through human and machine collaboration, we achieve augmented intelligence that drive ethical and adaptable solutions. Importantly, AI is not about replacing humans, it's about partnership. Machine can excel at handling scale and speed, while our human can bring ethics, creativity, and context to guide these decisions. So together, machine and human, we create a powerful synergy for making progress. In short, this fourth industrial revolution isn't about machine takeover. It's about amplifying our human power. So AI will replace many routine and repetitive tasks we have already witnessed, such as manufacturing, assembling, lines, data entry, and the standard analysis, even basic customer service, and so on. It also will even take on some entry-level professional tasks, including legal document review, radiology interpretation, and even the entry-level code generation. By automating these activities, we hope AI can free humans to focus on more complex, more creative, and strategic work. So what AI will not be able to replace? So in my view, like AI will not replace human-centered roles that require empathy, for instance, nursing or social work, nor the vital work of education and mentorship. And more importantly, it cannot replicate the creative and strategic thinking essential for innovation, product design, or ethical leadership. Similarly, AI cannot fully manage systems, integrating tasks like interdisciplinary problems, solving, and complex project management. So these areas rely on unique human qualities, our compassion, our creativity, our judgment, and the ability to navigate complexity. So here, among these three bullets, we can see I highlighted the second and the third one. So these are the areas rely on our engineers. So we really, the growth of the AI in the future need more engineers and tech innovations. So what's next? So we have seen this AI is advancing at lightning speed. And my hope is this AI could handle all my housekeeping chores like cooking, laundry, washing dishes. And so I could enjoy things like music, gaming, reading, painting, so on and so forth. But the reality is AI has mastered all the things I want to master, like music, gaming, reading, and painting. But it still cannot do my course. So I feel like at this moment, what we hope AI to do and what we hope we can do, like looks like the role are switched. I want to do these top things, but AI did that much better than us. And I hope AI can replace me to do all my housekeeping stuff, but it still cannot do that yet. So from this perspective, my thought is really AI, there is a gap of what AI can do and what we hope AI can do. So specifically, I think we need have this embodied AI technology. So this AI can perceive, can act, and interact with the physical world. So essentially, AI can replace us to do the things we really don't like to do. So embodied AI, our engineers will play a critical role in innovations that enable this so-called embodied AI. So what does it mean, like AI being embodied? So if we take a look of our human, so what make our human intelligent? So as human, we use our sensing organs like eyes, nose, ear, mouth, etc. to sense the environment. So we have these sensing organs to collect information from environment. We have our neural system, our brain, to process all these, collect the sensed information and generate knowledge. And then we can use very highly compressed language to exchange information and knowledge, and then use this knowledge to make real-time decisions and take actions. So similarly, for artificial intelligence, our engineers need to develop all these things, including develop sensing technologies to collect the data, all kinds of sensing, computer vision, sound, and like even biosensing, so on and so forth. And then we need to process this data using signal and language processing, as well as analytics. And our engineers need to apply machine learning to generate meaningful knowledge from all these big data. And our engineers also need to design communication and networking systems to share this data and insights efficiently and effectively anywhere in the world, hopefully. And finally, we need to create control mechanisms that can use this knowledge to take intelligent actions and make real-time decisions in a sensible fashion. Okay, so these opportunities make engineers very essential to this AI revolution and to enable this embodied AI. So here is a small test bed developed in our lab. So our objective is to convert a remote controlled car. So this is originally a remote controlled car called F110. So each dimension is 1/10 of the real F1 racing car. And we want to change this into a more intelligent autonomous robotic car. So to make these things happen, so we remove the original like control unit of this remote control car. Then we equipped it with sensors such as LiDARs and camera to collect information. And we use NVIDIA Jetson NX processor. This is the brain of this car to process the data. And we developed the algorithms allow these cars to, say, avoid collisions, plan routes, and compete with other cars on the track. And these decisions are sent to this VSEC motor controller, which control the car's motor and the steering server. So this Wi-Fi antenna enables the robotic cars to communicate with external systems. So now we have this car which can sense, which can process data, which can exchange information, and which can make real-time decision based on the sensed environment. Okay, and with all these functions, the robotic car can explore the environment and optimize its driving. And we have also organized a few racing events, and our students really enjoy to play with these cars to see how it interact with the environment, to explore it, so on and so forth. Okay. And actually, like making car drive in this very well controlled environment, the racetrack is quite relatively straightforward. Our like undergrad students can do that, but that's not enough. So we want to have this car to operate in real environment like a human drive the car. Okay, but to make this car have the brain like human brain to handle the complex real-world environment, this is really a big challenge. Our human drivers must understand the traffic rules and the regulations before we can have our driving license. So autonomous vehicles must also be fully aware of things like local traffic laws. For example, in British Columbia, right? If we drive on the road, we see a blinking green traffic light. What does that mean? It means the signal will remain green for some time. We do not need to slow down, right? So, but in Ontario, the same signal. So if the green light blinking, it means it will soon turn yellow. So you can see like the same signal in different places, they have different meaning, which means we need to understand the difference in the specific locations, their local traffic laws, so on and so forth. While it is very straightforward for human drivers. So if I go to Ontario, I need to be aware, oh, there is a change in these signals, so on and so forth. It's very easy for us to understand such rules by language exchange or read a written policy. But the challenge is to equip the autonomous vehicles to have the same level of contextual intelligence. To achieve this, we found we can leverage this large language model to enable intuitive communication between human and vehicles, to provide a contextual understanding from diverse sources such as traffic rules, accident reports, and perform untrained tasks using zero-shot or few-shot planning, and continuously learn and adapt to individual user preference to improve driving over time. However, this vision of apply large language model to do autonomous driving actually presents significant technical challenges. So it drives our work on new training architecture, algorithm for computing and communication resource sharing and optimization, and advances in prompt engineering and orchestration. So in these slides, the right-hand side, this is our recent design, which leverage cloud, edge, and the vehicle computing resources to collaboratively train and fine-tuning large language model for autonomous driving. The benefit of this large language model-based autonomous driving lies in its generalization, or a better capability to deal with many long-tail cases. What does these long-tail cases mean? Okay, so long-tail cases refers to the long list of very low probability, very rare, unusual, or edge case events that don't appear frequently in training data, but are very critical for safety. So if we ignore that, we may end up with very dangerous accidents. So LLM-based autonomous driving is much more capable than the previous supervised, unsupervised machine learning models in dealing with these long tail cases, and has much better generalization capabilities. So here we have some experimental results using this CALA simulator, show that our LLM-based autonomous driving solution can handle many complex real-world scenarios, require sophisticated perception and decision-making, like whenever we see the pedestrian coming in this figure A, we can slow down. or in figure B, we found oncoming traffic, but it's not in our, it's in opposite direction. We can know how to share the road with them, so on and so forth. Okay, so given the time, I want to keep on. So in addition, in addition to this road autonomous vehicle, given our Earth has 70% of the surface covered by water, so I'm more enthusiastic than to apply or embodied AI technology to explore this ocean. Like in Victoria, we are surrounded by this beautiful ocean. So this gives me the question is, yeah, when I take a look of this ocean, how do I know that if this ocean is really healthy, like a rainforest, or thick, like a desert, right? So we really hope our ocean is such beautiful places. We have a good variety of biodiversity. But the reality check is not so promising. We found that overpopulation of sea urchins in many sea floors near West Coast from California to British Columbia. The reason is this sea urchin eat up all the kelp forests, and these kelp forests are crucial for many other marine species. So when we have this overpopulation of sea urchins, so the whole area of seafloor looks like a desert. So that's really depressing. And the scientists have many questions that need to be answered, density of these sea urchins, and so forth. So it really pushed us to do some seafloor monitoring. But the seafloor monitoring is extremely expensive, like human diver cost expensively, and the research vessel even cost more. And in Victoria, we also have this largest underwater sea observatory, but we found this current fixed location installation of these devices are not enough. Like more than 95% of areas are uncovered by these fixed locations. And these fixed location devices sometimes will attract or deter animals, make the observations skewed. So the game changer should be the autonomous underwater vehicle like ROVs. But the problem is the current ROVs, majority of them are not smart enough to do this autonomous like exploration. So in our lab, we have a bit working on this. We develop our autonomous ROV. Yeah, this is our recent test. We want to have ROVs to form a team. And so the two ROVs can keep certain form and not too far away from each other and follow certain planned paths from certain initial position to some destination while they maintain this teamwork. Yeah, experiment shows they can achieve both. The location can converge to what we want. And sometimes we also need to handle the situation. We have obstacles to avoid. So while maintaining the formation, we still need to avoid some places. Yeah, the results shows like we can achieve our goal. So these are the very beginning efforts of to make sure like we can have this intelligence not only to vehicles on the ground, but also vehicles on water or even underwater. And we believe, we believe that these are the areas that embodied AI can really help our human for a better future. So we can see this embodied AI can help us to explore places otherwise we hard to explore, like ocean and space. It also can help our healthcare and the life scientists, which will contribute to many positive climate and sustainability technologies and transform our business and industry and so on. So given the time, I want to stop it here and thank you for your attention. If you have any questions, I'd be happy.
Yeah, thanks, Professor Tsai, for the nice talk. And there are several questions from the audience. One asked that you have commented that AI will not have the same intelligence as human beings have. So what's the rationale behind this statement? Because many people are afraid of non-controllable development of AI in the future will ruin our world. So what do you think?
Yeah, I think I cannot say AI will not as smart as human in all areas, but first of all, the AI as a technology, they do not have their value or ethic or the meaning. Right? It's human who will define what is good, what is bad, and we will define the loss function or cost function, etc. So essentially, our engineer and our human will be the one to define the good and the bad for the AI. So this ethical guidance is always depends on human. And of course, like we needed to make sure, like from the day one we designed this AI algorithms and so forth, we needed to put ethics of humans into our design to make sure like AI will be our partner rather than our foes. So the complexity and the intelligence of AI is because of really the AI do not have their own say objectives. Most of their objectives is like coded by human, right? So if AI don't have such motivation, it's a human who will motivate AI to do certain things. So how our humans' curiosity and motivation will drive humans to think of more complex, more forward-looking problems. And this is something I believe AI is not ready to compete with us.
Yeah, and the second question is also related, as AI may greatly reduce the need for most coding, writing, and data analysis jobs, leaving only a few senior places, and future opportunities will likely demand higher entry barriers, such as advanced graduate level training. What option or paths do you see for the majority of the displaced workers who may not be able to reach this threshold?
Yeah, this is a good question and a tough question. And I think if we take a look of example of the animals, right? So in the world of bird, like the most silly bird, I think the low intelligent bird is chicken. Yeah, they can go out of egg and immediately live independently and handle all their need until they die. But the intelligence level of chicken is really low. It cannot do much more intelligent things. And the contrast on the other side is raven. Raven is extremely smart, but raven needed to being educated by its family for 5 years before independence. So raven can even use tools to solve problems. Yeah, raven can do these social activities they group together to achieve certain tasks. So in the future, I believe same things for human. Because our human needed to deal with more complex, more challenging environments, our education will be prolonged. So we should not stop at the simple level, like a coding, or simple level, like something being replaced by the machine. We needed to spend more time in our lifetime to study until we can reach certain complexity to compete and to outsmart the machines.
Okay. Yeah. Thank you very much. And thank you for the talk. Yeah. We'll move to the next one. Yeah. So the next talk will by Professor Li Deng, and he is well known for his excellent contributions to the AI and in particular deep learning applications. He's a fellow of the Canadian Academy of Engineering and a life fellow of the IEEE. He was a professor at the University of Waterloo and the chief scientist of AI at Microsoft in Seattle. He received the 2019 IEEE SPS Industry Leader Award for leadership in pioneering research and development on large-scale deep learning that disrupted worldwide speech recognition industry, and for leadership in natural language processing and finance engineering. In 2015, IEEE SPS Technical Achievement Awards for outstanding contributions to automatic speech recognition and to deep learning. He currently serves as the Chief AI Officer at a quant firm headquartered in New York City, and his talk will be on one simple equation that runs across neural speech recognition, computer vision, and quantitative finance. Let's welcome Professor Deng.
Well, thank you very much for organizing this workshop. I'm very appreciative about having this opportunity to share some of the thoughts that I have and also some of my earlier experience in AI to everybody here. So I'm choosing this special topic that is a little bit different from what other presentations I've heard on AI. I want to use, since this is an engineering workshop, right? So I'm allowed to use the equation, to describe, part of the, the content that I'm going to share. And this is, very simple equation, but it has fairly powerful implications throughout multiple areas of artificial intelligence, including neural network-based speech recognition, computer vision, and quantitative finance. And that I probably will spend a few minutes introducing. So that's myself. I spent 10 years at Waterloo. I enjoyed that very much. And then I moved to Microsoft. Initially I spent about 2 or 3 years on leave from Waterloo, and I decided not to return. And during Microsoft time, I actually was able to work with some, the best people around, actually from Toronto as well, Professor Jeffrey Hinton, working on voice recognition before everybody got to know how powerful speech recognition, how powerful neural network technology was about. And then I moved, I left Microsoft about 8 years ago and moved to a different industry, also working on intensively on AI, different applications. So this presentation, it's a very short presentation. So this presentation is meant to last for 1.5 hours. So I'm going to compress it down to half an hour. Basically, there are 2 parts. One is the high tech part about deep learning, which also I call the modern AI. Right? That's essentially deep neural network, as well as a whole bunch of extensions of the earlier versions of deep network that I'm going to share with you. And the second part is to share with you some of the quantitative finance part, how that area has been also been impacted strongly by deep neural network. I'm going to distill these 2 big areas of application of the modern AI into something that can be described with a very simple equation here. Everybody knows that in the Nobel Prize goes to AI, or last year actually, and the whole reason why Nobel Prize in physics goes to AI is because, according to Nobel Committee members, well, as a matter of fact, there's a committee, I think it's the chemistry Nobel laureate, Nobel Committee member. There was some interesting discussion that I was participating in, going to know exactly why they gave this Nobel Prize, in both areas of AI, in chemistry as well as in physics. And part of the reasons for physics here is that the Boltzmann machine, right? And that is the opportunity that I had the opportunity to work with Professor Hinton directly about 15 years ago during my time at Microsoft. So now let's flash back about 15 years ago, and this actually workshop took place in Whistler, Vancouver, Whistler area, where this is the first time the deep neural network was intensively discussed in the area of speech recognition and related applications, including natural language. And I was actually organizing that work with Professor Hinton as well as my colleagues here. And about 3 years of the intense work, and voice recognition get totally disrupted by this technology called the deep neural network. And we wrote this paper together, published in IEEE here. And at that time, before deep neural network entered into voice recognition, speech recognition, the standard technology is what's called the hidden Markov model. This is the generative model, the one that that Professor Tao was sort of mentioning earlier in his presentation. And this is a very nice a generative model, and it had at that time it had been around throughout the history of voice recognition until then, until about 2010, 2011, and then in combination of neural network and hidden Markov model, it actually just changed the entire landscape of the whole field. And that actually took place between 2009 to 10 and also 11, close to 12. We worked about 3 or 4 years. And basically the problem got mostly solved. And soon after that, computer vision got disrupted in the same way, using the same kind of neural network, but using a little bit different kind of neural network. And subsequently, natural language processing, the whole field was also disrupted. That happened in 2015, 16. And then throughout all this time, I was at Microsoft in charge of many very important projects, not only in voice recognition, but also in translation and various other projects. And most of those problems got really solved, totally solved by deep neural network. And later on, of course, transformer become much more powerful. They actually solve the problem in a much bigger scale, entering into what's called the generative model. So essentially, the old days of, at least in voice recognition, is based on generative model. It's a hidden model. It's a shallow generative model. And then deep neural network to change this whole field into deep discriminative model at that time. It's called a sequential discriminative model. And then soon after that, since 2017 and 18, 19, around that time, the GPT came around and actually turning the deep neural network into generative model again. So it's a very interesting history to go from generative model to discriminative model, coming back to generative model. But now there's some tendency of some interplay between generative model and discriminative model together. You heard Professor Dachan Tao's presentation about technical difference between the two, why certain kind of combination could actually produce something that individual type of paradigm will not be able to produce. But anyway, so this is the progress in this area up until 2012, and then the error rate just dramatically dropped from a very high error rate all the way down about a human level. This is the architecture at that time, but currently, up until now, the basic architecture is still very similar, very deep model, but model become much larger. And OpenAI has this whisper approach that actually following very similar kind of design philosophy. And there was a very interesting book written about some of the earlier work so this book covers the stories up until right before ChatGPT came around, about 2012. There are a lot of historical background, for how the deep neural coming from the winter all the way to the hot summer. So 2012, that was I think one of the earlier media coverage about the deep learning success. So our Microsoft research, working with Professor Hinton's work, was prominently featured in this, in a full page New York Times article, and then soon after that, everybody uses that, including computer vision, and the computer vision breakthrough image that happened about the same time here. So now I'm going to reflection back of some of the early work I myself did at actually at University of Waterloo, and that has some connection to the current work that that actually is related to computer vision and natural language processing and ChatGPT. I'm going to share some of this kind of the thread starting from earlier days. And that actually is the paper that I wrote with my student and my colleagues at University of Waterloo. It's about 2000, it's about 29. This is actually one of my early PhD students work together with me. So at that time, we started using neural predictive models that actually has a very deep model, but it didn't really do as well as hidden Markov model at the time. There's not much GPU in the 90s. GPU. I think NVIDIA was just starting at the time. No GPU there. Which is the standard computing to try to solve the voice recognition problem. And actually, I remember the second author here. I think he's a professor now in McMaster University. But we have not been in contact for a long time. And he actually implemented some of the technique in this paper. And Professor Jeff Hinton happened to be his external examiner, right, in Ontario. PhD student had an external examiner around here. But that was the early exploration of the neural network. And then the key of this work is to show that if you were to use a neural network as a predictive engine in the time series manner, that's similar to the kind of problem to what speech recognition is about. By the way, quantitative finance that I'm going to share with you later also shares similar kind of temporal structure here. So the technical content of this paper is as follows. You have a linear prediction. Everybody knows that, but very, very simple. It's kind of auto-regression model. And in the early days, people use a linear auto-regression model on the right-hand side over here. And then it, of course, doesn't do well because if you analyze the temporal properties, like memory capacities of this model, it actually exponentially decays in terms of the memory capacity here. And then we know that language and speech has reasonably strong memory in terms of temporal structure. So linear prediction model, everybody knows that it's not very good. So this is the baseline, right? And then when we use the nonlinear prediction model, and this is very similar to the auto-regression model, the one we see, the decoder, right? Nonlinearity, you get neural prediction. So we actually use the neural network. At that time, it's a shallow neural network, it's about 3 layers, to predict the next frame. It turned out that the memory property is slightly improved. And there are some analysis we have done at the time to show exactly how the memory can be improved. And then we actually also, that was about 30 years ago, that paper. We actually also developed a technique to combine linear prediction and nonlinear prediction as a joint prediction for the next time frame. Once you have the prediction model, you actually can do almost everything, right? Just like ChatGPT can now. But in early days, like 30 years ago, we actually used the joint prediction model to predict the next frame in voice. And once you have that prediction, you actually compute the scores of the prediction from which you can do recognition, but in a generative way. And then it turned out that if you mix linear model and nonlinear model as a joint prediction, you actually get much better memory. You can see that in this graph. This memory, they are all decaying, but it decay in a much slower manner than using either purely nonlinear model or purely just linear model term itself, which are shown over here. But anyway, the whole point of showing this result is not to show that this is, it's good model. It's just to show that it has certain kind of property. However, during that experimentation in the old days, we just couldn't get the final recognition rate higher than hidden Markov model, so we gave up. So, and then I totally switched to hidden Markov model with scaling properties. Hidden markov can be scaled up very nicely as well. But the result, was improving. And when I moved to Microsoft, I was using hidden markov for a in a very productive way during the first 8 years. And then until 2008 and 9, I was able to invite Professor Hinton to come to Microsoft to work with me directly on deep neural network, essentially replacing this large sort of term of nonlinear prediction here using very deep neural network, and the result become much better. And then, of course, at the time, we throw away linear term here. It's just because, the idea here is that nonlinear model is supposed to incorporate linear as a term, but it turned out that that's a not very nice thing to do, to give up on the linear term. Until 2015, when the residual neural network, got published, they actually used exactly the same equation as the one that, like 30 years ago, that we used the linear plus nonlinear. And that's actually the same equation, simple equation that uses linear and nonlinear term as a separate mechanism in the additive term to predict the next time frame, whereas in the residual neural network is to use to predict next layers of the very deep neural network. And mathematical equation is almost identical. Of course, the physical interpretation are different. One is to time series forecasting. The other one is to use these two terms to predict the next layers in the deep neural network. If you turn the layer into the time series, it will be identical. But this has a huge amount of impact in computer vision. But in terms of mathematical underpinning of this neural network, it actually has the same kind of prediction in linear versus nonlinear. And the reason why this one works well, according to this paper, is that it enables optimization to be much more efficient. So the gradient doesn't get diminished. Whereas in speech application, we interpret that at that time, the same equation as having a better memory in time. So these two mechanisms seem to be a little bit different from each other, but in reality, they are actually converging to the same just wonderful result here. Now I'm going to switch the gear to this new application here. Now, before I do that, let me summarize what I just said here. So the same equation here, linear versus and plus nonlinear. The linear equation part, it doesn't even have the parameter here, but it's a kind of skip, connection. But if you think about t to be either the layer or the time, you actually can think about this equation to be something like linear and nonlinear joint prediction. And the nonlinear part has a huge weight matrices in the neural network. And this one can be as big as you want. And it turned out that the current, the best neural net model, the transformer, has this architecture built into the system as well. So this equation started about, we did actually University What to Do research. We did about 30 years ago. Now it's the same equation now in the transformer part of the system here. So just to summarize, in speech recognition, the same equation is used to demonstrate that it has a longer and more powerful temporal memory than the standard hidden markov model, and also than the standard purely nonlinear neural network prediction. Whereas in computer vision, this mechanism is shown to have better optimization properties, give rise to better optimization result for learning the very deep neural network. That's called because it solved the gradient vanishing problem. And these two mechanisms inherently have some deep connection to each other. Now I'm moving down to a new application. It's called the quant finance. Here, let me skip all this. Okay, so the basic quant is a quantitative research, and that's actually a quant industry is something most people wouldn't know in engineering, right? Until recently when DeepSeek model came out. about 6 months, 8 months ago, since last year, the end of last year. And actually, that DeepSeek model originally came from a company called Huangfang. That's in Hangzhou, China. So a lot of people get to know about this. And I have been working in this field for about 8 years. So the basic model is what's called the capital asset pricing model, CAMP model. Essentially, it's a linear model. So basically, this is the factor. Sometimes if people go to factor model, you get 3 factor. So the early days, the model is called. It's actually around 30 years ago. And this model actually, I think, got Nobel Prize somehow. It actually uses various factors to predict the asset price, stock price, or bond price, or whatever price it is. And that the early, I think it's in 70s or 80s. So one factor model. The factor is the market, right? And then later on, it developed into 3-factor model, and then it's about 7 or 8 years ago, it got about almost 100 to 400 factors, and that's actually the standard model that the finance industry. It's an all linear model, and then one of the things I did, it was to bring this deep neural network from Microsoft at the time into Wall Street, finance. So I was actually chief AI officer of one of the largest hedge fund it's called the Citadel in the Wall Street there. So basically, I introduced this neural network to be part of the forecasting in exactly the same way as using mixed linear model and nonlinear model to predict the stock price, for example. But so if you actually use the standard factor model for finance, that's actually what happened before neural net went to finance, about 2017 after I left Microsoft. So I was probably, we are probably the first group to actually use the standard linear model here with the nonlinear model. And the nonlinear model we call alpha. In the old days means over 7 years ago, before neural net got introduced, the alpha component really is kind of noise, right? You think about so many different firms use different ways of forecasting what kind of very, very noisy signal called alpha. And then when neural network became well known to be good in voice and image, people started to say, gosh, you can use the same kind of neural network to forecast what kind of very, very noisy signal called alpha. And once you do that, you actually come up with exactly the same equation as we saw in speech and in computer vision, right? The residual neural network kind of a way. And they turned out that this is the residual network block is actually exactly the same as what we're thinking about, except if you interpret the beta coefficient to be constant, you actually get exactly the same equation here. And that's another way of looking at the simple equation that runs across not only voice speech recognition, computer vision, but also it actually runs through quantitative finance. So let me summarize this. So the alpha now, rather than being modeled as a noise, now we can use a very large neural network to model the alpha. And then the conventional wisdom in statistics is that model capacity versus the size of the training data, there's a trade-off between the two, right? But all this conventional wisdom has been disrupted by the way that neural network actually gets applied here. It actually shattered, the conventional wisdom in the same way as in high tech. So let me skip this part. Okay, so at the end now, this is a little bit too complex here. That's some finance paper. They actually talk about neural network. But anyway, so let me give you a summary here. So we have the same equation here. The whole point of this equation is that you use the right-hand side linear and nonlinear mixed term to predict whatever left-hand side is. Right? If the left-hand side is the next frame of speech, then you get the voice recognition application. If the left-hand side is the next word in the neural network, you get a transformer. And whereas if F is transformer and the left-hand side is the next word, you get the ChatGPT, right? And then if the left-hand side is the next layers properties in the computer vision model, you get the residual network that actually is what's called the is essentially the key equation in the residual network. I think this is one example, one simple equation that runs across 3 different application areas in AI. So let me stop right here. Thank you very much.
Okay. Thanks, Professor Dan, for the excellent talk, and that's a very exciting history review and also very insightful discussion about one equation that predicts so many things. So several questions from the audience. So one thing is that it seems that for AI research, you need a very good background in mathematics. But for one that with no very good background, very advanced background in math, what can they do?
Okay. Well, actually, my answer to that question is that I think it turned out to be just the opposite. So to run neural network, you need 3 things in math, much simpler than many other fields in the old days, right? You need, the key is that you need to know some basic calculus. Therefore, you know how to do backpropagation. And the second part you need to know is the linear algebra. And the third thing you need to know, which is much less required now than the traditional machine learning, that's the probability and statistics. And with those, that actually can do all sorts of neural network than what we are doing now. So it turned out that the mathematics requirement is just much less now than about 10 years, 15 years ago. When I was at Waterloo, I was teaching statistics probability, very advanced, doing stochastic, latent models, for generative model, very complex. Now it's much, much simpler. So I actually prepared this presentation to one of the interns, in finance. And people are surprised, right? Because people normally think that in the Wall Street, you do very, very, martingale properties, all this, mathematics. People, coming from MIT, from Harvard, they expected to learn. So once they listen to this word, they say, gosh, we didn't even know that math is so simple. So it turned out that advanced mathematics requirement for neural network engineering is just so much less than in the old days of machine learning.
Okay, that's good. Yeah,
that's good news for everybody, right?
That motivates everyone.
Yep.
And in particular, people from other fields. And another question is that, finance is, it seems to be a much more complex system than the traditional speech and the image. In particular, the behavior of, say, a quant company can affect the market. So you predict the market, but if you do something, and the company is big enough, or the action is big enough, you can also affect the market.
Yeah.
So how do you deal with that?
So this part is very complex. Well, that is market impact, the interactions, competition, right? It's a game theory aspect. But that part has not really been explored too much. In the traditional finance, people have not been able to successful either. So there is a hope that advanced AI will be able to do that. So there's a standard saying that whoever's smarter wins the market, right? Now we think that ChatGPT probably smarter than Gemini, or Gemini could be smarter than XAI. So a lot of discussions as to whatever kind of smart machines you can put together, in order to win the game. And that's something very secretive. Everybody is exploring that. We don't have any good theory on that. But in terms of running the machine themselves, it's just much simpler, right? But the emergent behavior, wisdom, and the kind of emerging behavior, the intelligence coming out of those, the large language models are, I think, eventually going to win the kind of war you're talking about.
That's cool.
So this is a very deep issue. If you just want to beat traditional quant, you don't need to have very complicated math. And it turned out to be much, much simpler. but the number of parameters will be much, much bigger. Right? And that's more of engineering challenge than scientific and mathematical challenge.
Yeah. And the last question is that the recent large language models, do you think this will have big impact to?
Yes, very much so.
Yeah.
And then there's the multiple ways, right? So actually I skipped a couple of slides here. One of the major challenges, well, actually there are three major challenges in the quant. They can all be very well handled by large language model. One is the very noisy data, like alpha, or the alpha I mentioned at the end. It used to be treated as noise. You can model them, right? But now with the deep neural network, the noise become the whatever noise term, alpha term become much less noisy because you have very large amount of data to handle that. Sorry, the very large amount of the data and the very large number of the parameters in neural net to handle them, and that's one. And the second part is the diversity of the data sources, and that's something more very, very much engineering issue. So it's perfect. It's much less scientific than engineering now. So and when I was doing at Microsoft at that time, right, I was able to deal with image data, speech data, and text data, and also some tabular data. Very simple. About four or five types of data. Now in quant finance, it's much wider. For example, satellite image data coming into the picture, and also tabular data and time series data, as well as voice data. They're all coming into together, and that's another kind of challenge. But that challenge is also very well addressed by deep neural network. The third challenge actually turned out to be called the adversarial, nature, non-stationarity of the problem. That's very different than speech and language, right? In speech and language, the non-stationarity isn't as strong. It changes every now and then. Like for language, right? Normally the language behavior of the people actually changes, year by year. But typically, I mean, at least in the US, when you get a new president, a lot of news data changes, right? And it's very slow, right? Historically, the style of the language changes very slowly. Whereas in finance, it's very fast. Every day, market changes, right? And that part, it's very hard to handle. And that's actually the core issue in quantitative finance that are not in the high tech. And if you are mathematics oriented, you should think about that kind of problem. This is a very difficult problem, but it doesn't have a very wide application besides finance. Right? So this is something that for those people who are really interested in entering into finance, and that's kind of very interesting research problem that has not been solved yet. Yeah, okay. I think I'll probably just stop right here.
Yeah, that's cool. Thank you very much, Professor Deng. Yeah.
Okay. Thank you, Professor Liu.
Yeah. So now we move to the last talk of this session by Professor Majid Barhami. So Dr. Barhami is a professor of mechanical engineering and Tier 1 Canada Research Chair in Alternative Engineering Conversion Systems at SFU. He is a fellow of the Canadian Academy of Engineering and the American Society of Mechanical Engineers. Barhami's championed interdisciplinary collaborative research in multitude of sustainable clean energy systems, including harvesting and transforming low-grade heat for sustainable air conditioning, thermal energy storage, atmospheric water harvesting, heat pump systems, and dehumidification for applications in automotive, agri-food, sustainable city, and hybrid thermoelectric microgrids. He has a strong record in successful collaboration with national and international research institutes and industries. He formed 2 startups, won national and international research and innovation awards, published 12 patents and 350 publications, and supervised 180 highly qualified personnel, including 8 professors. So welcome, Majid.
Oh, thank you very much, JC, for the kind introduction. Can you see my slides?
Yeah, I can see and can hear you.
All right, wonderful. Good day to everyone. I'm pretty sure you're coming from all over the time zones. So as JC said, my name is Majid Bahrami. I'm a professor of mechanical engineering in Simon Fraser University, British Columbia, Canada. So I'm going to give you an overview from a different angle about AI. I'm not going to talk about the equations or the digitalized aspect of the AI. I'm going to look at it from the energy aspect. So what I'm going to talk to you about is what if AI could grow food and decarbonize cities? All right, so let's just start with the what if questions. So what if we can use the AI waste heat and we can use it to grow our food, decarbonize our cities, and create local jobs and strengthen our communities? And what if we could tackle obesity, improve physical and mental health, and build resilience in the face of climate change, while still providing the digital world with AI? So in this talk, I'm going to talk about why we need to be worried about the energy consumption that AI has, data centers, hyperscalers, and what can we do actually to use that, upscale that waste, to convert it, to upgrade it, to create services and get something valuable out of it. So in this talk, I'm going to present some of the research that we're doing in the lab, in our lab, and some of the pilot studies that we're doing to use this waste heat for the purposes that I just mentioned. So let me first start by giving you a picture of what's going on with food security crisis that we have in Canada. This picture shows some of the challenges we have right now. In 2023, we imported more than $5.6 billion in fresh vegetables and the same amount, more or less, in fruit. So with this high import dependence, the Canadian food system is vulnerable to climate change, trade disputes, tariffs, and geopolitical instability. Currently, we have the food insecurity problem. Almost 1 in every 7 Canadian households are affected by this food insecurity. And the climate variation, the changes in weather, extreme weather, and environmental volatility disrupts the production and distribution of food. And we also have a labor shortage that can also widen the problem and contribute to the raising costs. To put things in perspective, we grow a lot of fruits and crops in Canada in greenhouses, and about 30% of the cost of growing crops in greenhouses are associated with energy. The cost of labor is almost the same. So this will give you a sense of the importance of, especially in a cold climate like Canada, the importance of energy system. This actually can be true for hot climates. In fact, in climate like southern United States or in Australia or places like Middle East and Africa, where the climate is hot, the same problem exists, but they do not need heating. They need cooling to create suitable climate for growing crops. To also put things in perspective, the increase in household food cost would be about $1,000 extra a year by year 2030 because of the climate change and changes in the challenges we have right now. Let's shift gear and talk about the challenges that we have in our cities in terms of climate target. In a city like Vancouver, which is probably one of the cleanest cities in North America, buildings, natural gas usage for heating in buildings is responsible for about 54% of carbon emissions. And to reference this for you, cars, trucks, and transport sector only contribute 39%. So buildings and heating in buildings, that's the same, again, the same problem exists in hot climate, but instead of heating, this becomes more or less the same number. It becomes cooling because you need air conditioning, are a major issue in terms of carbon reduction and our meeting our climate goals. And all cities around the world, countries around the world, in Paris Agreement, we all signed up to this treaty. So the goal of this agreement is to reduce our carbon footprint in cities by half by year 2030. And then the goal is to become completely carbon neutral in cities by 2050. So that's a huge task in burden on municipalities and residents of these cities to also consider. So I'm sort of painting a picture of the energy needs that we have and the challenges we are facing in Canada, but more or less the same challenges exist everywhere. Now, you hear these days everywhere that we need to change to electrical systems because it's cleaner than burning natural gas or oil or fossil fuels. But I want you to look at this plot, and I'll explain to you why, in my opinion, this is probably not feasible. So basically, the question we are posing here is, would electrification alone solve our climate and energy crisis? This figure shows the data from the United Kingdom, Britain. One of our colleagues collected the data. The curve at the bottom, you don't need to be a scientist to understand this curve. It's very simple. I just want to explain to you what does it mean. The green curve at the bottom shows the day-to-day energy consumptions as is. The data shows the period from 2015 to 2021. More or less the same trend exists these days. You see the grid goes up and down slightly. When you add the electrification of transport sector, this is shown by the blue curve in the middle. You can see that right off the bat, you need a grid that has twice the capacity than the existing grid. Then the red curve that goes up and down like a sinus curve shows the scenario where you change all the natural gas boilers and fossil fuels in buildings and convert them to heat pumps, electrical heat pumps. This shows almost 3 times capacity increase. More importantly, you can see that the load changes radically from winter to summer because, for example, in Britain is a heating load kind of grid versus for example, in India, you have a cooling load variation system. Again, the same principle applies. So you need, if you consider these two, 2 times 3 is 6. So you need a grid almost 6 times bigger than the existing grid just to keep up with the electrification that stems from electrification of cars and trucks and also heating, cooling for buildings. Now, why am I telling you this? Because the data here does not include the need for AI and the data centers that are emerging rather dramatically. So this is a perfect storm. I don't think any grid can, at the moment, do this. Even if we have all the clean electricity, let's say we master fusion, we have all the clean electricity that we want. Even with that, just designing and building a grid that can distribute this much electricity in highly dense populated areas of cities is almost impossible. That requires major infrastructure, takes huge amount of time, regulations, and nobody wants to see a distribution facility in their backyard. Now, why Canada is uniquely positioned for AI data centers? I'm going to argue that we stand at the point of dramatic shift and a significant growth, as was discussed in today's workshop with my colleagues. This is a fourth revolution, right? So there would be a lot of these facilities built and it would change everything that we do. So Canada is uniquely positioned for AI data center location because we have a cold climate, which creates an environment that makes it easier for cooling data centers. We have an abundance of clean and affordable electricity. Majority of our electricity comes from hydro, which is completely clean. And we have a stable democracy, and we have the skilled workers. So I think we, especially at this point, because of all the trade issues that we have and uncertainties facing our economy, I think we can and we should look into attracting more data centers in Canada, which is also the case anyway. Now, so I was talking about a couple of slides ago about the stress on electrical grid, and I'm sure most of you guys know that I mean, there's no secret here. AI data centers are growing dramatically. So in the US, the estimate is that is going to be about 12% of the total electrical consumption. More or less the same trend exists all over the world. So if it, I mean, in 2023 alone, we have 10% jump in electrical consumptions globally, and it's going to only increase. To put things in perspective, it actually helps to understand what does 12% means in terms of the actual electricity consumption. Agriculture as a whole sector, including production, distribution, and all that, transport, it counts for only 1% in the US. So this is a huge amount of energy that are going to be used in data centers, AI. So why not do something with this? So data centers to be one of the largest waste heat sources. If you don't know what waste heat is, energy has not only quality, but quantity, but it also has quality. Waste heat is referred to sources of thermal energy with temperatures more or less than 100 degrees centigrade. This threshold shows basically indicates that you cannot really do much with this energy. This is the still energy. So data centers receive electricity and do their thing, and then they need to dump the heat out as waste heat. So the amount of energy remains the same, but the quality of it changes. So it goes from high quality electricity to waste energy, which is waste heat, which is actually a pest. So you need to get rid of it. There is a huge demand these days on developing heat sinks and cooling management to eliminate or remove the heat with GPUs and other computing devices. That's actually a major hot topic in thermal engineering. But what I'm trying to do here to show you that now we have all the AI coming, and this is happening if you like it or not. So why not use the waste heat from the AI to do something useful? So waste heat is not only generated in AI. About 60% of our energy is eventually converted to low-grade heat and is wasted. This is the largest untapped energy resource on the planet. So it comes, as I said, from AI. If you go to any of these power plants, fossil fuel or nuclear power plants, you see tremendous amount of waste heat. In fact, about 60% of the amount of energy content in the fuel becomes waste. You also have garbage incinerator, geothermal sites, cement factories. So you can actually get the heat from the sun. So the list goes on and on and on. Oil and gas are major waste heat generators. Pretty much anything we do generates waste heat, and that's thermodynamics. This is the second law of thermodynamics, or entropy. I'm sure you heard of that. And so my research has been focused on harvesting and upgrading waste heat. So developing technologies, cycles, material that can use waste heat and to do something meaningful. I need to mention something very quickly here. So it's called waste heat for a reason. It usually exists in places that is hard to recoup it, and it's also very low efficiency. And put this in context, so far the cost of energy, primary energy, like fossil fuels and so on, has been very low. So that makes it less interesting for companies and researchers to focus on that because there's not much incentive. If the electricity cost is cheap or natural gas is super cheap, nobody really wants to go through all the length and deal with these low-grade heat. Now, with the AI, I think we have an opportunity. So, okay, let me talk about a little bit. I'm not going to show any questions about what we do in the lab. This is mechanical engineering and perhaps not interest to you. I'm going to talk about the concepts. So there is this group of technology, we call it sorption technology. This will enable converting and upcycling waste heat into essential building and greenhouse services. So over the last decade or so in my research lab, we developed a number of energy conversion cycle, energy storage systems, and that includes material, advanced composites, heat exchangers, reactors. So with waste heat, we can provide cooling and heat pumping. This is double effect to cool or heat a space. We can capture CO2 from air to create and enrich CO2 for accelerated plant growth in a greenhouse or vertical farm or other applications, say in soda fabrication facility, you need CO2. And we can do also dehumidification to maintain optimal climate. And we also have a technology that can harvest water from air for irrigation or for industrial application using only waste heat. And we developed a thermal storage system that can store heat or cold for round-the-clock operation. So what is the sorption heat transformer? It's a cycle. This is basically an alternative heat pump. Again, what is a heat pump? If you don't know what a heat pump is or air conditioner, you have it in your house, in your fridge, or in your car. This is a machine that moves heat or cold from one source to another source. If you look at the nature, the heat always goes from high temperature source to low temperature source. That's the natural way of heat transfer. If you want the heat to go the other way, from cold to hot, that is a air conditioner or heat pump. And that requires energy because you're going against the nature. So this machine, I mean, the heat pumps need energy. The electrical heat pump that you use in your house or fridge use electricity. Our heat pump use heat. As I mentioned in my, in my talk right now so far, again, electricity and heat are both forms of energy. Is that the only difference is electricity is a higher quality form of energy. You can do anything you want with it, including doing computation, versus with heat, you can only do a space heating, right? Or if you have a system, you can generate power. So you need to do more tricks with heat to get the energy out of it. So this system includes, very briefly at a very high level, I'll be more than happy to share more information, and you can also visit my lab webpage. We have a number of publications that you can download and read about this technology. So this, at the core of it, it has a sorber bed here that has a specific composite that we developed. This material is highly porous and likes, let's say at this stage, water. And it can absorb water at a significant amount. To give you a sense, we can absorb about 70% of the material mass water. It's a huge amount of water. So the material is basically made out of abundantly available material. That's one of the key. This is a sustainable material. So silica and some hygroscopic salt. So if you heat the material, of course, let's say the water inside becomes evaporated, goes to this heat exchanger. Let's say you call it condenser. You cool it with the ambient. You store the water. This is a closed loop system. So you can store water as liquid. And then you have this material, we call it charged. And if you reverse the process, the material will absorb the evaporated the water in evaporated form, vapor, that generates a cooling effect on the evaporator side, on the bottom figure here, and a heating effect on the bed side. So you can use it for heating or cooling, depending upon the application. The beauty of, or the feature of this system is that this material can work with waste heat with temperatures less than 90 degrees, 80 degrees centigrade. We're actually working to reduce this to lower temperatures. I'm going to show some other application of this for CO2 capture. So as I said, it has this system has 4 major components: 2 reactors, a condenser, and evaporator. Over the last 10-15 years, we developed a number of innovations to improve the efficiency of this cycle, thermodynamic cycle, to upgrade waste heat. I'm not going to go through these details. Again, they're available on my web page. I'll be happy to send you more information. Now, I want to show you some practical application of this. So we have this project with the city of Burnaby, which is a major municipality in Greater Vancouver area, where our university is. The city is building a major district heating system, and this is going to use the waste to energy facility heat. So in Vancouver, we have, like any other city, we have a lot of garbage. So this facility collect the garbage, about 260 tons of garbage a year. They burn the garbage, and this is like fossil fuel, but it's called sustainable because you're not digging the ground to bring the garbage. If anything above ground is a circle, right? A circular economy. So they burn the garbage, they get the electricity, and that powers about 16,000 homes. The waste heat has been so far unused. The city of Burnaby now had a major project. This is one of the largest infrastructure district heating systems in North America. It's going to cost about $1 billion by the time it's finished. So they're installing large pipes. Think of it as a central heating system for the city. So the buildings will receive heating that comes from not fossil fuel burning, but from burning waste. So this will practically decarbonize the city of Burnaby. So it's a very high, for those of you who haven't seen Burnaby, British Columbia, this is one of the most highly populated cities in Canada. By 2030, this would be more highly densely populated than Manhattan, New York. There's a lot of high rises being built in that area. So the city took the initiative, build the infrastructure, installing the pipes right now to use the waste heat to decarbonize. Again, the reason I'm mentioning these is we can use waste heat from data center to do the same thing. So data centers would be, if not more than garbage incinerator, would be on par. They're building I'm sure you hear all these days, more and more data centers are being built across the globe. The hyperscalers, they use like half a power nuclear reactor energy, and they all become waste heat. So imagine you can, decarbonize the entire city of New York by a data center, a hyperscaler. Right. So we have this pilot study right now with the city. City is building this infrastructure, as I mentioned. So they're going to meter the heat. They sell it to the homeowners or the buildings in the city. They don't need me for this. This is easy. Anybody can do that. So what we are doing, our sorption heat transformer is going to use the waste heat in summertime, where the system will sit idle and do pretty much nothing, to convert that waste heat to cooling effect and basically create a double service and more than double the revenue of the city. So this will create sustainable air conditioning for buildings where they have access to waste heat. So you may ask why not for individual cities? What happened to buildings that they do not have access to district heating? And my answer would be they can also use this. They can install thermal solar panels on the roof, or if there are other plans, there are so many other different versions of these district heating systems across the world that they use. They burn wood chips or use waste heat from power plants. There's so many actually in Europe. If you have a chance to search it, you'll be surprised. But by using waste heat and converting it to cooling, we are eliminating the electricity that is used and also the problems with the chemicals that are used. This technology uses water as refrigerant, so the refrigerant is not contributing to ozone layer depletion or greenhouse gas emission associated with that. So at the moment we are halfway through this pilot study. I'm going to show you a very short video to show how this system works. So at the moment, we are pilot testing this small scale prototype at the City Hall in City of Burnaby. This is open to the public and consultants and builders, developers to come and see. This will be on display until September 5th. We picked this time of the year because it's typically hot and humid in Vancouver, although not as hot and humid in other places. But this actually shows the system works. There is no moving part. There is no harmful chemicals, and the machine only uses waste heat. At the moment, we are using temperatures around 80 degrees centigrade in this machine. Obviously, this is a demo technology prototype to show the technology. This will be scaled up when we get to next phase. So as I said, this is a 5-year project. At the moment, we are at midway in the project. We are here showing a pilot study. And then hopefully next year, we are going to build a larger scale and then showcase it in a community center. The picture above shows the engineers from the city and my postdocs engineers in the lab with the prototype. Gives you a sense of the size of this small scale prototype that is enough for a 1-bedroom apartment, basically cooling right now. Right. So we are also using, we're working with several major crop manufacturer, greenhouse operators in Canada. So as I said, in order to grow crops in a greenhouse, you need to create a suitable environment that has really temperature control, humidity control. I talked about how do we manage the temperature, heat it or cool it using waste heat. Here I'm showing you another technology we're developing that controls the humidity using waste heat and also can capture CO2 from ambient air and enrich it to boost the growth using waste heat. So again, imagine if we design and data centers and co-locate them with greenhouses, or if this is outside the urban area, or install it. And if this is in the city, you can work with district heating system to use the waste heat, or if you're outside, you can use greenhouses to use that heat to heat the greenhouse, grow crops, control the humidity, and control CO2. To give you a sense of the problem that we are facing in Canada right now, CO2 is a must for any greenhouse grower. They inject CO2 into their greenhouses. in Canada and most of US, because natural gas is so cheap, they burn natural gas and push the exhaust, blow the exhaust, the flue gas of the boiler into the greenhouse just for CO2. Again, imagine if we can use a data center based heat. That's the only data I'm going to show you today. This shows the data center, the base heat that we developed for CO2 capture. We are using the heat that is generated typical temperature that's generated in the AI data center, 60 degrees centigrade. So if you give me 60 degrees centigrade, we can increase the CO2 concentration to about 800 ppm. And that's, again, to put in perspective, a typical air that you and I breathe is the CO2 concentration is between 300 to 400, depending upon where you are. But the greenhouses use, they need between 800 or 1,000 part per million. And this data shows that using waste heat, and this small reactor that I'm showing is a small proof of demonstration. We are working with some companies, hopefully, to scale up this and pilot to study this soon. And again, you can also store heat using the same material. That will actually help. If you have waste heat at some time, but you don't need it, you can store it and upgrade it to cooling or to heating and use it later on. That's another option with this technology. So this energy storage, think of it as a thermal battery, provides energy storage densities 20 times higher than the traditional hot water tanks. This is actually, in fact, we are on par with some lithium-ion batteries in terms of energy storage density. The difference here is we are storing heating or cooling, not electricity, and this does not need any rare earth minerals or lithium or any harmful material. And this is also suitable for long-term storage. Yeah, I want to paint a picture for you. This is an article I came across in Iceland. Iceland is a very cold country, similar to Canada. There is this village called Reykholt with a population of 100 people in the middle of Iceland, near their capital city. But they are close to a hot spring. There's a lot of geothermal in Iceland. So they built this is a small business, family-owned business since 2001. Friedheimer farm, they use the waste heat from a hot spring with artificial light. They grow more than 2 tons of fresh tomato per day. So they improved and they grow. At the moment, they had 6 greenhouses, and they also grow herbs and so on. One thing I actually I like to touch on is the dining experience they have. They sort of evolved into a community hub, and they build a new greenhouse that not only produces tomato, but also it serves as a kitchen, bar, and like a community hub. People in cold, dark winter time come to this greenhouse to have parties and socialize, and they also work. So this to me provides a vision. So this is something that we can do in Canada. Of course, we have access to waste heat from a variety of sources, including geothermal sites like Iceland, especially in BC. But AI and data centers can be that waste heat, especially with the scale they have. They can easily, again, to put things in perspective, we're going to have 12% of our electricity be consumed by data center. We only need like 1% of that to, cover the entire energy. So there's more than enough heat to grow our food, anything you want. You can pretty much grow anything in the greenhouse, including bananas and avocados and even coffee. beans and so on. So there's no shortage of actual waste heat needed to do that, and then that would create to me a different approach to circular economy and how to integrate data centers not only as a digital tool that consumes a lot of energy and may put people out of work, but also as a beacon of hope. This could be generating not only income from the IT part of it, but also from cooling the cities, and also growing crops, generating jobs, creating community hubs that help people, fighting winter blues and anxieties, and then the sustainable job. These jobs are sustainable. You cannot export these local jobs. So I want to finish with again, the vision to sort of summarize what I said. So AI going to be producing a lot of waste heat, would be a big chunk of our primary energy going to AI centers, data centers. So why not use that to strengthen our agriculture food sector to secure a sustainable future, and create green jobs in the community and generate hubs, decarbonize buildings and cities using waste heat, and ensure food security, and build a climate resilience community, and in the meantime, improve physical and mental health by providing fresh fruit and vegetables, and also areas or community hubs for people to socialize and enjoy the society more. With that, I'll better stop and see if you have any question.
Yeah, thanks, Majid. So there were several questions. Yeah, one is that what are the main challenges of reusing waste heat from data centers, given that those data centers often located in semi-rural, naturally cold areas with limited nearby heat demands?
Right, that's what I mentioned, the greenhouses, right? So true, most of them will be installed in rural areas, but even rural areas, you can grow crops. At the moment, I've been helping city of Revelstoke, which has a huge, and this is, for those of you who are not familiar with that, this is a ski resort town in British Columbia that has a major hydro dam, and they're designing one of the hyperscalers there. There's a huge amount of electricity because electricity is cheap, and they're building that. And the population there is, as I said, very small. It's like this city in a village in Iceland, right? So again, if you read this about this, what fascinated me about this village is 100 people population is this town, but that actually this little 6 greenhouses there has turned into a agrotourismo. So people from all over Iceland come, and all those other tourists, international tourists, come and visit this. They're actually growing, they're doing franchises and so on. These models can help. And again, as we enter into this era, policymakers should be aware of this. And in my humble opinion, why we're building these AI centers, data centers, why not co-locate them with areas that we can at least use the waste heat and contribute to, circular economy? I hope I answered the question.
Change
Oh.
mic or on mute.
Sorry, I cannot hear you, Daisy.
Oh, yeah. So, thank you for sharing the multiple initiatives on energy reuse. Could you elaborate how you envision the business model for AI factories to adopt those ideas, and what are the economic impact? Yeah.
Very good question. I mean, do your imagination. Think about this. They're going to make their money from selling, IT services. and waste heat at the moment is a waste. So they can donate it to community and then help their image and give back to the society. So this waste heat energy will become a major catapult for a variety of technologies that as I mentioned, like growing crops and so on, or they can charge a fee for this. Still, if you consider using electricity to heat the city or cool the city or do CO2 capture and so on, the waste heat would be a fraction of the operating cost. Given still, I mean, these technologies are still in the lab scale or earlier stages, so that requires investment, and that's true for any new technology. But if you eliminate the operating cost, the energy cost, the environmental impact of new technology compared to old one, I think there is a very good business case to make in order to bring these technologies to the market. And also you need to include the social impact, as a social and health impact of creating these facilities and jobs as well.
Yeah. The last question is sort of related. It is you have partly answered that, but the person particularly asked, you said that by 2030 the AI will account for 10% of global power consumption. So can you elaborate more about the rationale of this?
No,
behind-
I'm actually citing that's not my, AI is growing. This is an expectation. This is a forecast. And I cited the source, so I cannot really defend it. But from what I've seen, everybody's seen, in 2023, we saw a 10% jump in electricity consumption. I'm sure you all hear Microsoft and Amazon are building nuclear power plants, buying and all these power generating facilities to address their energy demand. So this is real. Energy demand exists. How much? Even 5%. As I said, at the moment in the US and Canada, the share of agriculture energy is like 1%. Even if we can harvest that, that would be a major impact.
Yeah, that's good. Yeah, there are a lot of questions, so we can also wait for the panel, and then we can have more discussions. So we have a 10-minute break, and then we have the panel at 10 o'clock in the West time and 1 p.m. at East time, and then we just have a break for 10 minutes. Okay, thank you. Yeah.
Thank you, JC.
Yeah, that's that.
So welcome to the last session, the panel for future engineering. This panel will be moderated by Professor Jesse Chu. He's a fellow of Royal Society of Canada, a fellow of Engineering Institute of Canada, a fellow of Canadian Academy of Engineering, and European Academy of Science and Arts. He's a distinguished university professor from Western University, have over 600 journal papers, 77 patents, and supervise over 200 graduate students. And he is the CAE board director and also leading the international committee. Actually, he initiated this symposium and worked a lot for this symposium. And let's welcome Professor Jesse Zhu to moderate this session for the panel. Yeah.
Hello, everyone. Can you hear me?
Yeah, we can hear you.
Okay.
Let me get my video on.
Okay. Hello, everyone. I'm Jesse Zhu here. Thank you for introducing me, Dr. Chuan Liu. And we now have the panel discussion. And I'd like to discuss, to introduce the panel members right now. And they are Professor Majid Bahrami from Simon Fraser University, Dr. Lin Cai from University of Victoria, and Dr. Li Dong Quant from New York City, plus Dr. Vincent Wang, and who is from okay, see here, yeah. Professor Wang is a professor in the Department of Electrical and Computer Engineering at University at UBC. Vincent Wang received his PhD with distinction degree from the University of Manitoba in 1994, and then he got a master in applied science from the University of Waterloo in 1996, and PhD from UBC in 2000, all in electrical chemical engineering. From 2000 to 2001, he was a system engineer at PMC, Sierra Inc. And in 2002, he joined the Department of Electrical Computer Engineering at the University of British Columbia, where he is currently a professor. His research area includes wireless communication system, mobile networking, Internet of Things, smart grid, and energy system. Dr. Wang is the editor-in-chief of the IEEE transaction on wireless communications. He has served as the area editor of IEEE transaction on communication and IEEE Open Journal of the Communication Society, associate editor of IEEE transaction on mobile computer, and IEEE transaction on vehicular technology. And Dr. Wang is Dr. Wang was an IEEE Communication Society Distinguished Lecturer. He also received the 2022 Best Paper Award from IEEE Transaction on Mobile Communications. And Dr. Wang is a fellow of IEEE, fellow of the Canadian Academy of Engineering and Engineering Institute of Canada. So with that, now we have 4 fellows, and as moderator, I will probably start with 1 or 2 questions to get things started, and let the panelists answer first, and then we'll start questioning and answers from other people from this talk. Okay, our panels. My first question is that there have been several waves of AI in the past. This new wave has been here for over 10 years. Is it another type coming, another hype coming, or not in the near future? If you could, somebody could answer that. Maybe each of you could quickly comment on that, and then we can move on.
Yeah, maybe I'll just offer. Can you hear me? I'll just offer some
Sure.
my own opinion. Yeah, I think it's not hype. I think it's just beginning. It's just tip of the iceberg. There are a lot more is going to come. Yeah, so especially for people working in the industry, it's much bigger things is going to come within the next, several months or maybe 1 year. There's a fundamental change in the paradigm, right? So a lot of people in the presentation, I heard generative model, distributed model, or AI. And that's a much bigger wave that actually started a few months ago. It's called the agentic AI. Not only AI actually can generate the content, but also it actually can execute the intention, not just understanding what's going on. It actually can execute. Some of the presentation, like robotic, is part of the agentic AI. You can think about generative AI, the one like large language model, is the brain. Right? the brain that give you some intelligence. And then agentic AI give you the tools. It's like a hands. You actually can do things. So the old days when we could generate this conversation chat, you can say, oh, I want to book hotel, I want to, book flight, I want to reserve a restaurant. Now the agentic AI allowed you to physically book the hotel, give you the receipt, negotiate the prices, understanding, not just understanding your intention, your preference, but also actually execute, book things for you. And this is just the very, very beginning. Yeah,
Okay.
that's my 2 cents.
Thank you. Thank you, Dr. Dunn. Other panel members?
Yeah, I cannot agree more with what Dr. Dunn's vision. Yes, like this is the beginning of what I mentioned, the first industry revolution. Like as a researcher myself, I have been shocked by how powerful this new wave comes. And the students nowadays, actually the good ones, becomes much more productive, much more efficient, because they can use this AI to learn faster and can solve problems much more efficiently. And the same thing could be used in industry, in business, so on and so forth. So this is definitely not a hype. It's something will change our society fundamentally.
And I also agree as well. And other presenters already given different applications of the use of AI in different domains, including finance, energy systems. In the area of telecommunications, there are also a lot of advances in this area. How do we make use of different types of sensing data, multimodal sensing, and actually to perform better resource allocation. And apart from that, even what Dr. Li Deng mentioned earlier, agentic AI is also many applications in telecommunications area as well.
Thank you. I think we have all wrong answers. My next question is, what's Canada's role in promoting AI in future engineering? Are we a leader or we're behind? And this is a very dynamic field, and Canada is in a unique position.
Yeah, I want to jump in. Sorry. Yeah,
Sure,
I want to jump in first because I want to thank Canada's funding system, particularly NSERC. Without NSERC support, like this new wave of AI, so this like Professor Hayton and so on. At the time, nobody else like support this kind of research. Canada's funding agent did a good job to carry on these initiatives and make it happen. So I think definitely we have, Canada have been lead in some aspects. And right now, I think Canada also in a very unique position that we are a country with such a large landscape. We are lack of human powers overall. Our human density is so low. So the AI, particularly physical AI, embodied AI, agentic AI, will be extremely helpful for Canada to not only survive, but also advance in the future global world. And I think we have such a good opportunity here. So the thing is, we need to team up globally, leverage the global market, be open to the outside input, so on and so forth, and to keep on invest on these AI technologies and make us a leader in the future.
Great answer. How about other panels?
Yeah, as a proud Canadian, I actually would consider that Canadians' contribution to AI proportionally, per capita is much greater than everywhere else. You think about it, right? The initial, push for adopting deep learning is coming from Canada. And it's just NSERC system. When I was at Waterloo many years ago, 30 years ago, 25 years ago, Canadian funding system, I think, is better than most other places. People actually are, encouraged to explore new ideas. And of course, a lot of the U.S. Funding agency will argue that you need to have critical mass to do big things, but those big things should be done by industry, not by academia. So how to separate the innovation from university? You just have one or two good ideas that can change the whole world. That actually started this new modern AI started from academia from Canada, and I think this contribution is just tremendous. With the belief that certain, technology will take over. Yeah, I totally agree with Professor Chai's comments about Canadianism. I'm so glad that Canadian funding system still sustain the similar kind of funding pattern that I was experiencing about 30 years ago.
I can quickly add to this very briefly that beside the AI as a science, the software aspect of it, in Canada, because we have access and we possess huge amount of clean renewable energy, we are primed to host data centers, hyperscalers. We don't need to generate dig the ground to get we also have access to largest biomass, wood chips and forest products that can be used to generate clean electricity to power the AI data centers. So again, it goes back to policy and how the government, federal government and provincial government ease up the permits and encourage investment. So like I actually at the moment I'm working with a couple of companies, working with them to see if they can get some of these in Vancouver area. There are a lot of hurdles for these companies to invest. So that would be, again, I'm not sure if CAE can expedite the process or voice these concerns to not only the federal government to improve these regulations, but also help attract the investment to host these data centers. Thank you.
I guess for the question by Dr. Xu, whether or not Canada is a leader in AI, if I rephrase the question in a different way, whether Canada is a leader in AI research, Dr. Deng already mentioned that for many years in terms of per capita, Canada is indeed is a leader. But if we take a look at a different perspective, if you take a look at some of the top conference papers published in top AI machine learning conferences, we will notice that papers from other countries, including US and Canada, in terms of numbers, and also in terms of one way to measure that is the number of citations is also higher. It's good that NSERC is and other funding agencies providing funding for pure machine learning research, but it's also important that Canadian government also provide funding for applied AI techniques for different research disciplines as well, so that we, in all different industrial sectors, we can all benefit and also advance from the application of AI in different domains.
Any additional comment on this? Okay, there's one question coming from the audience. One fellow said, could the panelists suggest a single most important capacity that a graduate engineer should have in an AI-enabled workplace. This obviously matters for the student and professors, and perhaps even more matter to the employers of those students. So let me repeat, I think it's asking what is the single most important capability a graduate student should have facing the AI world. Thank you. Questions?
Yeah, so let me offer some opinion here. I think the most important capacity should be that eager to learn. It changes so fast. The whole field changes so fast. Just being able to keep track of what's going on, to have curiosity of trying to understand what's going on. I think it's probably the most important character. Apart from some basics, as I said earlier, the mathematical foundations, for the model AI is just much weaker. It just doesn't require a lot of very, very deep mathematics. Not like, the machine learning. Right? In the old days, machine learning 10, 20 years ago, the student have to get so much, preparation in order to be able to get into machine learning and AI. At that time, AI wasn't even popular. Now with the neural network, it just, we already, both academia and industry already determined that this is probably the only way to go to AGI to change society. And then the key really for students to be able to make the impact to the society, to the industry, or to their career is to be able to have the curiosity, to have the eager to actually pursue along this direction. And I think this is probably the most important skills that people, being able to learn how to learn. And this is probably the most important goal from academia, from the universities.
I guess on top of that, I fully agree. Eager to learn is very important. But in the given the pace of AI, I think learn things fast and this is also very important as well, because sometimes by the time they understand how it works, the field is already advanced to a different level.
Yeah, that's important. You have to be fine. And another related to what both Professor Wang and I just said earlier is that the skill, this is a new skill that wasn't during my time at Waterloo, right? I was teaching signal processing, how to solve equations, how to and many of those skills are not as important as the newer way of looking at the application of AI, about how to express the goals, the objectives, the nature of the project you are working on in a way that can be understood by AI. And namely, this is natural language, right? So the humanity training, I think, should raise their profile compared to many years ago, right? So when I was at Waterloo, people usually say that, humanity, social science, they are not as cool as engineering and natural science. But now I think humanity should be able to raise the bars. I would suggest that if I were to change the curriculum, I wouldn't, for computer science, I wouldn't actually even encourage to have students to learn. In the old days, I was teaching C programming, Fortran programming. I remember in the old days. Now, those are just not as important as being able to use the English to precisely describe the goal of your project, the nature of the problem you want to solve. And that, how to break down the problem into pieces, the critical thinking. And this is the kind of skills I think now in the AI area is becoming more important than in the old days.
Yeah, I echo that. Critical thinking is really important because, often the AI cannot make good judgment by themselves. Sometimes they will have some results which is collusion, so on and so forth. So it's humans' critical thinking and judgment that will be important to guide this AI to generate things towards what human needs and what's benefit for our society. So I think I fully echo like what has been said. Self-motivation for learning and critical thinking for good judgment are critically important in this AI era.
Yeah, critical thinking and the ability to express and to sort of communicate the thinking into your colleagues and into AI system. Think about AI system to be a team of the experts that can help you solve the problem. You need to express your problem, and then to be able to have the interactions, with the AI system, just like you have interaction, with human beings. And that skill is actually, it used to belong to the humanity world, right? They train speech communication, to train how to do, writing. I think these skills should enter into engineering much faster than we normally would imagine.
Okay, so far we have very, very interesting discussion. Now there is another interesting question from the audience. It said, in reference of the July White House Americans AI Action Plan, would our panel members able to share your view on Canada's engineering and policy sector? How should they focus on advancing AI infrastructure, streamlining regulations, and aligning internationally to stay competitive and secure? Basically asking, the US has this AI action plan, how we could cope and, strengthen Canada's position. Anyone want to start? Ling, you want to start?
Yeah, this is a tough question. Like, I think every country nowadays want to gain some competitive edge in this incoming AI era. Not only US, China, and everyone want to be the leader. I think from government point of view.
Yeah, go ahead.
Yeah, go ahead. Yeah. From government point of view, they have this trade-off whether they need to hands off or hands on, right? So whether they need to have more regulation to make sure like the AI technology developed is under certain agenda from the government policy or not. I think at this point, I hope like our governments could be of course fundamentally have some regulation in terms of make sure like the AI generated is follow our humans benefits and ethic-wise follow certain standard. Meanwhile, a bit hands off in terms of which direction we need to specifically go and what kind of collaborations we can do or cannot do. I think have an open research environment and allow us to explore all kinds of directions could actually be much more beneficial than use the government as a pointing stick, pointing this is the things everybody should be focused on, so on and so forth. I think in this aspect, hands off might be more beneficial to us.
Yeah, so I thought that Canadian institutions can contribute to AI safety and regulation simply by not regulating within the country, but also contributing to the international efforts. That I think this kind of regulation should be at the international level rather than individual countries level. And US basically action saying that it's hands off, because if you constrain too much, other countries will exceed US. I'm actually neutral to the current US plan. There's a positive part, but also there's negative part, right? I think this AI safety regulation has to be done in the international environment rather than individual country. And Canada can contribute to that much more so than regulating Canadian system itself, right? Which is just less productive than contributing to the international regulation. It is very dangerous if you are not careful enough, right? Nowadays, I have to wait. So every time I read something, I didn't used to be that way, right? I just usually, you know the source, you think that it's good, right? But now you can't, right? Even if they can even put the source information to be fake as well, right? So it actually takes a lot of effort for you to, it put additional cognitive burdens every time I do some reading in the social media, especially. And that's not very good, right? It wastes a lot of people, some people who are not actually, who do not have critical thinking very often will fall into prey, right? Be cheated, be fooled by the fake information. And that's just a tiny bit of the danger that what we are facing immediately.
Any comment from other members? No. Majid?
No, I agree. And again, at this stage, everything is dramatically changing and so fast, we can only speculate. And again, this is above my pay grade. Probably policymakers should, and the government, should look into this as opposed to us scientists and engineers. The fact is, AI is here, is going to penetrate vertically, horizontally in everything we do. The best we can do is to prepare and then roll with it. Thanks.
Okay, next, I'm trying to ask questions from the student point of view. If I'm an engineer, I want to learn AI. I realize there's some fundamental knowledge about AI, like theories, logarithm and other things, but also the application side of AI. So which side is more important to a new student, coming to the school to learn something? Would he need to learn both, or he would concentrate on one or the other? And the background thing is that how those are connected. Your guys as an engineer appear to be all doing the application side, but are you learning a lot from the theoreticians? Working on AI theories, big data. I don't know. So, anybody try to answer that?
Yeah, so having been in this field for so many years, right? So my advice would be that there's one area you really as a student, don't have to spend all of effort into. That's kind of pre-training of the network. The pre-training is a very, very big area, but that's 100% it's industrial and also big industry. Well, even for application oriented industry, people don't even if you know how to do that, you won't be able to play any role unless you are hired by those companies to do the kind of project. So pre-training. So basically, the AI, there are a few areas. One is pre-training, one's post-training, and the other one is the application. Three part. And I believe that that's my personal view is that for graduate student, I would spend 50% of the effort on post-training part of the what call the theory, the algorithm. And then the other 50% for whatever application area you're interested in, either in finance or in robotics or in communication or in maybe in image, autonomous driving application. At least you need to spend 50% to understand the intricacy of application. Otherwise, you won't be able to apply. But at least, substantial amount, maybe less than 50% of the effort for one aspect. This is the most important aspect of neural network, large models. That's post-training. After pre-training is done. But pre-training, scientifically, procedure-wise, is a very strange. It's very simple. It just predict next token. Right? It's very like that equation I showed earlier. You predict t plus 1 or layer plus 1. But you just the whole intricacy of that effort is to have huge amount of data, just like you train a baby. Right? Train a baby, it become reasonably smart. It has the capacity to be smart, and then you have to train them. That's called post-training to give specific, instances, algorithms, That's called reinforced learning, and that part doesn't require huge amount of engineering resources, and university student can do that, and that's actually a very large amount of AI field. A substantial area of the AI is called a small model or medium model, not large model. Large model is very hard to train. So that small model, medium model, or large model with post-training, those are the ones the graduate student or the engineers are not in the big companies should be able to contribute. Not only contribute, but also learn and advance. And a lot of technology are in that area rather than in the pre-training area. Yeah, that's my advice.
Thank you. Other members?
If I just provide a general discussion for that, typically because my students they mainly work in communications and also energy system area, not in like pure fundamental machine learning design. So most of the time, I think UBC and also in many other universities as well, graduate students or undergraduate students, they simply take machine learning courses, which actually give them the fundamentals. And in my area, the important thing for the students is that they also need to be domain expert in a specific research area. And then try to understand which particular machine learning tool or model they should use and what are the advantages and also what are the drawbacks. One example is in wireless networking for a long time, even as of today, we try to solve problems by formulating as an optimization problem. And nowadays, a lot of people also try to use machine learning as a tool to solve optimization problem. But there are pros and cons as well. And I think using machine learning as a tool, say graph neural networks as a tool to solve optimization problem, or even some people now advocate use of large language models as well. So one particular part has to do with the fact that for a long time we look at constraints which are hard constraints, and nowadays sometimes people also notice that solutions that we obtain using machine learning models, they may not always satisfy the constraints. Of course, there are many techniques that can try to tackle that, but some of them, they can still give a probabilistic bound, but not a 100% guarantee. So back to your question is to do with the fact that for students, they have to learn the fundamentals about machine learning as a tool, including what Dr. Li Deng mentioned about which part to focus, post-training application, and then look at which particular tool which are good to be used for the problem. Thank you.
Yeah.
Okay, I have another question regarding work efficiency versus the ethics. There are more works to be replaced by AI. So there's the concerns about job security, job displacement, and how that could be balanced. Additionally, if AI is given too much autonomy, how would that affect our human lives? Which means how we adapt to the AI, ever-changing AI world, whether we're losing control. If we do lose control, what's the consequences?
Yeah, this is a very tough question here, right? Everybody has to figure out there. But I think if you are students, as a student, right, advice to students, if you are eager to learn, be adaptive, there should not be any difficulty, right? The worst thing is that you switch, very quickly switch to something else. So really the flexibility, adaptability, that's the key, right? Just like Professor Wang mentioned, learn some basics. And optimization is important. It's part of the post-training, the one I mentioned, right? And post-training include, understanding the why you design neural net the way it is, and how do you adapt the different architecture institute to suit application. And that's very important skill. We do that all the time, right? In industry. Not just using the standard open source code and then you just run it. If you do that, you don't know much, right? You don't go inside the model, and then try to think about better ways of optimizing them, interpreting them, all sorts of things that can be done. But I don't think that is conflicting with the job security, right? If you actually understand the basics, there will be new applications coming out that will require your skills. But if you are simply as a student, right? So some of the students that we talk with, we're interviewing for our intern. They simply, what kind of experience they downloaded open source code, they should run it, and then if the result is good, they are, they're happy. If they're not good, they have no idea why it's not good. And that kind of attitude is going to eliminate you in the workforce. But if you are curious to really understand why it works well and go inside the code, to modify the code, to run different experiments, optimize things differently, optimize neural differently, and then you can interpret the result differently, do iterative experimentation, understanding how the experimentation cycles looks like. And I don't think that kind of job can be eliminated easily. Yeah, that's my advice.
Yeah, I agree. Like when we see the past history, whenever there is an industrial revolution or something drastically change the society, they will wipe out many jobs, but meanwhile will create many more new jobs. So I think the future is something certain is the future is more uncertain. So it's no longer have this kind of job that you can learn something today and then apply that for the rest of your life. That's not feasible anymore. So I think the only thing our future generation, our students can do is it keeps on learning and keeps on adaptive and to face the change. And in terms of whether this AI will overrun the society and I think a majority of the people who working with AI will have certain concern, but not that much. I think there's still a big gap between AI over smart human at this point. So if we keep on learning and understanding, and we can keep up with the advance of the AI and understand eventually our humans' value will guide the evolution of the AI technologies and make AI a very powerful tool to be used by us, not just AI is something to replace us. So that's my opinion.
Okay, time flies, and it's already more than 40 minutes, and I hope we should close the panel discussion. At this moment, I'd like to thank all the members of the panel, Professor Tsai, Professor Wang, Professor Deng, and Professor Bahami, and as well Professor Ota and Professor Tao, who left us because of the time difference. And thanks all for their effort to have the very, very successful symposium today. As mentioned by Professor Liu, and this symposium is initiated by the International Committee of the Canadian Academy of Engineering, and I am the chair of the committee and as the director of the board of CAE. At this moment, I'd like to ask all the panel members and our audience if you could provide some feedback, not right now, through email or through other means, to tell us your reaction and reflection on this symposium. Whether it's very interesting, useful, and so we can decide whether we want to continue. But from the number of people attended, looks like there's enough interest, plus the number of questions being asked by the audience. So we should have enough audience. We should have enough interest. We have actually a lot of interest. And this is also our effort to go to international with the Academy, Canadian Academy of Engineering. So with that, we're also thinking whether it's useful to set up a working group for AI engineering in the under Academy, Canadian Academy of Engineering, because we do want to have more cross-linking, if I call it, between our fellows, so we can make the best use of the organization. So with that, I'd like to hand over to Professor Liu to do the final remark. By the way, thank you, Professor Liu, for organizing such a wonderful symposium with Professor Tao. It has been almost half a year. He has been working on that. Thank you very much. Okay, Professor Liu.
Okay. Yeah, thanks, Professor Zhu, for the conclusion. And it's my great pleasure to chairing this symposium with Professor Dashen Tao from Singapore. And it's a very interesting work and of course hard work, but with many people's effort initiated by Professor Zhu, and then with those speakers and also panel members, and then of course with the staff members from CAE who helped a lot with this event. Eventually it becomes so successful. And I also thank all the audience who listened to those kind of excellent speeches and also ask a lot of interesting questions. And we wish that we can continue this series and have it in the future. Thank you very much. And now I hand over to Robert. You want to say something? Thank you very much. Yeah.
Thank you, Jianshuan. So I would like to repeat the thanks to everybody who put this together. I found it a fascinating session. I would remark from Professor Kai's comments about the various industrial revolutions that, in fact, each one of those industrial revolutions also spawned a new field of engineering. And with Professor Deng as well, Dr. Deng, I can really see that this is going to be an area that we're seeing the birth of a new field of engineering that is very much wound into AI and how we use AI. So I thought that was quite insightful and an important aspect. In addition, just to having seen all these different areas that AI is getting applied to. So thank you so much for your time. Thank you for putting all of this together. I think from the perspective of the Academy, as Dr. Xu said, we're definitely going to be pursuing the idea of doing more AI sessions. We'll talk a bit about how we organize those, but would like to thank everybody for signing up and turning up for this session. It's always good for the panelists to see that there's interest and that people stick around particularly for these longer seminars. It's a big commitment of time. So thank you all very much, and hope to hear from you about this event. And by all means, comment on our LinkedIn page or send myself or the staff any comments, any things, ideas for future seminars, things we can do to whether the time spot's right, bunch of things, whatever you like. So with that, thank you so much, and I will, unless there's any final comments, I will sign us off. Thank you.
Okay. Thank you, everybody.
Bye-bye.